All right, welcome to another exciting week of statistics. So first thing we want to talk about is data project proposals. I know some people have been asked, have questions, so I'll try to, kind of go over it a little bit and then answer any questions that you have. So kind of put a due date of April 3rd-ish. So that's a little under a month away, so hopefully that's sufficient time. Big piece is to communicate with us. We give feedback on all the proposals, and if you don't get full credit, presuming you submit on close to on time, we're going to ask you to make revisions. So the goal is you should get full credit on the proposal. Our goal is to make sure you picked a data set and have questions that you can actually reasonably answer to achieve for the full project. There on the course website, there is a template you can download for the project proposal as an R markdown. You can just fill that in. So you could do that, or you can use whatever format you want. And there's actually an example data project here you can look at. So you could see it's kind of terse. We really just, it doesn't need to be verbose. It's long if you answer the questions, that's what's key. So we want to know kind of like what your broad research question is. This might get refined a little bit. That's often a big area we give feedback on. We want to know where the data came from, how it was collected, the type of study, and if it was observational experiment, probably most likely observational, but occasionally you'll find something. The source, so if you have a reference or at least a link to it, do highly recommend picking a public data source. It's okay if you want to use work data set, but it's a lot easier if it's something that you can just use publicly, because you might want to think of this as like something that may end up in your portfolio or something like that on a GitHub repo. Variables, I talk about that, response and explanatory. So we're just really getting in. And so tonight we're going to really formally talk about null hypothesis testing, which is one approach you could use. The other is regression. That's kind of a common way to do it. So these might vary. And then just some descriptive stats on your variables that you're going to have, including some visualization. So I think that should all be outlined here, and it's all in the proposal. Yeah, I think this is basically the same thing. So you can see that example. You can see a template that we have. So just to give you a sense of where you're going to, what the goal is at the end of towards the end of the semester, maybe Angela, we can meet before next week and set up the spreadsheet for sign up slots. So we usually have a smaller group, but we usually have like 6 90-minute time slots. Usually 3, I think we did like noon, 12 to 1:30, or like 7 to 8:30 on 3 different days. And so you can just you're going to sign up for one. So you're going to present your project and then see everybody else's project. We have a peer evaluation form that you could fill out, and then we consolidate all that together, and our feedback and your peers' feedback anonymously all together, so you can kind of see what other students are doing and try to make it a big learning opportunity. Did I miss anything, Angela? Now we can take questions. I think there's enough time you can look at this, spend a little bit of time this week, and obviously ask questions in Slack or bring them up next week if you don't have them now.
Yeah. Someone asked if they could make a Shiny app for the final project, and I think that we don't have a problem with that, but we suggest making sure it works before you do that.
We're doing a poster presentation in April at a conference, and we're going to probably create a Shiny app to kind of accompany it, so we can dig into. It's a great way to you can just have a drop down with all your variables and have appropriate data visualizations and stuff like that. Yeah, absolutely. If you want to do that, but that's above and beyond, but happy to give help and feedback on that. Any questions right now? Any burning questions? No. Okay.
Yeah, Jason.
Oh yeah.
Hey, just could we scrape data from a website? I mean, I
Sure.
guess the risk with that is it could change at some point, but.
So save a copy of it. Obviously if you're going to scrape it, save a local copy of the data. I mean, you can work off of that. You probably don't want to scrape it every time anyways. And you can just leave the script as sort of a reproducible example. That you just sparked something. It is absolutely okay to use the same data set that you're using for 607. Our goals are a little bit different than 607. So if you were doing, my understanding is Andy has a project similar where you might do some web scraping or some kind of other data manipulation piece. That's great. What we're really interested in is not the data collection part, but the actual analysis part. So you could use the same data set and kind of dovetail these two projects together. That's completely fine.
Is there anything you would discourage people from doing, or that you see that?
That's a good question. Let me think here. I think often the easiest way to conceptualize it, and what I always find tricky about talking about this now is we're only on chapter 5, and really the things you're going to want to do are what we're going to discuss over the next 6 weeks or so, 5 or 6 weeks. But you probably know enough about regression that if you're going to have some outcome variable that you want to predict from some other variables, I think that's often the best way to kind of evaluate whether a data set is good or not, or one you want to use. But there's plenty where you could do, a null hypothesis test like we're talking tonight. That's fine too, but I would encourage you to go a little bit deeper into kind of thinking about regression. I think what happens a lot of times is students think they can do a regression, and then we give feedback. It's like, well, a null hypothesis test would be better. Yeah, no pie charts. Yeah, please, no pie charts. I feel like they should go without saying at this point. I won't. I'm not. And on the project site, I have all right. So you can see the rubric. I hope we cleaned it up everywhere, because there was the template might say something to, one quantitative, one qualitative. So I have at least 2 variables. This may not always be true. You may just have if you're doing a null hypothesis test, you could end up with just 2 variables that you're really working with. So that's not critical. Just enough variables as appropriate for the data set and research question. I make sure to change that language. But there are some examples of some places to find data sets if you're having a hard time. I don't have on here, but a great place to look is Kaggle, which if you're not familiar with Kaggle, they host a lot of data science like competitions. And so they make data sets available frequently for various things, and you can, use those data sets, and that might even give you ideas of how to tackle it. Like, anyways, yeah.
Jason probably mentioned this already, but some you can also use if you have data from work. You can also use that.
But realize you're going to give a presentation to other students, so if it's proprietary data that you don't want anyone else to see outside your company, just be aware of that.
Yep. Yeah.
All right. Well, feel free to examples of great student projects. That's I keep meaning to, because it's always the end of the semester at crunch time. There are some great ones. Maybe Angela, we can look through even just in the fall. There are a couple that I know are real standout, but we can reach out and ask for permission to post them.
Yeah, it's a good idea.
Students generally do. I have to say, I have been pleased over the years. I hope this is one of the more interesting parts of this course, because you get to apply this to a topic of your interest. Have I done the John Tukey quote yet? So John Tukey, he pretty famous statistician of the last century, always said the best part of being a statistician is you get to play in everybody's sandbox, or sometimes it's quoted a little bit different. I thought he said sandbox, but I saw somebody else say something else, a different, like playground or something. But the idea is, I think, there. And I think you could substitute data science for statistics, right? There are data scientists in virtually every field. So And you can bounce around. I think I get a little, sometimes I get bored of topics. And so that has kept me interested in that I can be involved. Like right now I have two projects that are kind of, I mean, they're related to education some way, but one is on college entrance and one is, a youth studies program and trying to help youth inform changes in their communities. And they couldn't be more different in terms of goals and approaches, but the skill sets I use are very similar. So anyways. All right, let's talk about, okay, so 1 minute papers. I can't say a whole lot because there were quite a few missing values, so I might come back to it to see, and maybe it's really going to be better after tonight too, because we have 2 weeks for this. So let's go back to, I just want to revisit our uniform distribution. This is our population that we talked about last week. So we're going to look at this a little bit more. I am on the right slide deck, right? Yes. Okay. Right. So last week we took a random sample, right? And we got a mean. Okay. Right. And just to review what we did last week, what we talked about is like, if there's this notion of a sampling distribution, right? Which is if we were to take lots of random samples of the same size from the population, right? As the sample size of each of those samples increases, that distribution of means across all of those samples that we've taken will approximate the normal distribution. Okay. Then that's what the central limit theorem is saying. And of course, we can extend that. It doesn't just apply to means. We can use that. The theorem holds for median, standard deviation, variance estimates, all kinds of things. Okay, but mean is going to be the main thing we're going to leverage from that. Okay, so that brings us into this null hypothesis test. And I've already kind of mentioned this a few times, right? When we talked about the coin toss, right? We've flipped that coin 100 times and we'd expect roughly 50-50 heads or tails, right? And we wouldn't be surprised if we got 52 heads and 48 tails, right? And so the question is like, how far away from 50-50 do we have to be to say, that's unlikely, right? That's kind of what we're getting to. Now we're going to extend that a little bit further and say, well, is there a difference between my treatment and my control group, right? Angela and I have been working on this, things like this where we do randomized control trials, right? And so we want to know, is there a difference, or could that any difference that we observe just be because of chance? Okay. The way we structure this is using something called a null hypothesis test. And the null hypothesis is simply the status quo, right? I'm always tempted to use sex, but I'm going to try to think of something different. Give me, I did the treatment control. What, Angela, help me out here. Give me some kind of demographic difference. Oh, here's, I know one. First generation status, right? I was just looking at that. Here's one that's a little bit safe, right? Do I want to know if, college success is different based upon whether or not that student is a first generation student or not, right? This is kind of an important topic in higher ed and something we look at all the time, right? And so we could measure that like GPA, and so is there a difference in students' GPA? Now, I want to make sure I'm clear that I want to know if there's a difference. I'm not assuming that is a cause or not, right? So we are often going to do these null hypothesis tests, right? And the interpretation in terms of causality is going to be based on the design of the study, not the statistical test. So when I talk about null hypothesis testing here, I'm talking about it in terms of a statistical test that could be used to infer causality or not, right? And I just want to make that clear. So we got to go back to like chapter 1, where we talk about the design. The design dictates the interpretation, both in terms of generalizability when we talk about sampling or causality, right? And there was that 2x2 table that talked about, those kinds of things. So if we have a null hypothesis, then we have an alternative hypothesis. So using our first generation, right, I would say there's no difference in college GPA between first generation students and non-first generation students. So then my alternative hypothesis would be that there is a difference, right? And so we conduct a test assuming the null to be true to gather evidence as to whether or not we should appropriately reject the null hypothesis. Okay, we're not proving anything. Don't use that language. We don't prove there's a difference. We're just saying there is evidence to suggest we shouldn't reject the null hypothesis. And so there is probably a difference. But as we saw last week, and we'll see again this week, right, we're going to have to set a threshold. How much evidence is enough? We could always be wrong, right? And so so what we're going to try to do is quantify that. So the first way we're going to do this is using something called a confidence interval, right? So going back to our silly example here, where I just have a uniform population, and I drew one sample of size 30. So what I want to know is my null hypothesis is that the sample is 0.5, right? I could just pick a value. There are a lot of situations where you might want to do this. Like a lot of times in psychology, we'll give IQ tests, right? And IQ tests are designed such that they have a mean of 100 and a standard deviation of 15. So sometimes, so in terms of like, say, special education, they use null hypothesis tests. So they'll give a kid a IQ test, and if they score more than 2 standard deviations below the 100, right? So if they get a 70 or below, they would say, that might be how they classify, right? That's kind of a null hypothesis. Does the student score differently than what would be expected? Okay. So, I didn't update that. I want to do this real quick because this should be actually 1.96, not 2. So I think we talked about that last week. This is a remnant that I missed. So that will be knitting in the background. So because the sampling distribution approximates the normal distribution, we can use that. So what we could say is, well, if we take the mean of our sample, because we don't know the population mean. So we're going to use our sample mean as the estimate, right? And if we take the standard deviation of our sample, divide it by the square root of n, right? Remember, that's our measure of the standard error. The standard error is the standard deviation of the sampling distribution. So if we go 1.96 standard deviations below and 1.6 standard deviations above the mean, that covers 95% of the area under a normal curve, right? Why? So the integral from negative 1.96 to positive 1.96 is 0.95, right? So we got 95%. So that means we're allowing for like a roughly a 5% error, right? We would be correct 95% of the time using this as our confidence interval. And the way we interpret this, right, is our null within the interval, right? So the low bounds of the confidence interval here is 0.42. The upper bounds is 0.60, right? So 0.5 falls within that interval. So that means we would fail to reject the null hypothesis in this example, right? Because 0.5 given this interval would fall into that interval. Okay. If the value was less than 0.42 or greater than 0.6, then we would say with 95% confidence, we would reject the null hypothesis. Right. So here's what we're doing. So if we remember, the central limit theorem says that the mean of X is going to approximate the normal distribution, right, with a given mean. Now, of course, we don't know the population mean, so we're going to use the sample mean. Here's our standard error, right? And this is kind of how we calculate it all out. We can convert that to a z-score, right? So the z-score is going to be the mean observed sample mean minus our null value, in this case 0.5 over the standard error. And this gives us negative 0.204, right? So we already know from the standard normal, we'd have to go below negative 1.96 to kind of be, outside the range. But we could take this value and just put it in the p-norm function. I gotta do it. I do want to multiply that by 2, right? And that's going to give me my p-value, because remember, that's going to give me the area to the left, but I also want the area to the right. And this is what it looks like, right? So this is where our observed value was, or actually it might have been on the right side. What did we get? I forgot. 0.51, right? So we got this value, right? So we're going to take the area to the right and to the left. And so you can use this normal plot function and give it a critical value and actually see what it is. So what we're looking for to reject the null hypothesis is the shaded area to be less than typically 0.05, right? That's sort of been the standard for rejecting a null hypothesis. Now, there are situations like if you're in the physical sciences, it might be 0.01, might be a little bit more critical. In some situations, and because we're going to use null hypothesis testing when we get to regression and other kinds of prediction models, sometimes we'll say we'll keep something even if the p-value is 0.1 or less, right? A little bit higher than 0.05. So but 0.05 is common, what's commonly approached. So under these null hypothesis tests, right, this is just evidence whether or not to reject the null hypothesis test. So we're going to make a decision, but we could be wrong, right? So if the null hypothesis is true and we fail to reject the null hypothesis, right, that's good, right? If the alternative hypothesis is true and we reject the null hypothesis, that's also good. But we have a situation where if the null hypothesis is true and we reject it, right, that means we've committed a type 1 error. We call that a type 1 error. We rejected it. We said there's a difference, even though there really isn't, right? And this is often the focus of what null hypothesis tests. But you should also be aware that we could, if the alternative hypothesis is true and we fail to reject it, right, we would be committing a type 2 error, right? And like I said, in a lot of research and over the years, type 1 error is where things are, where we emphasize. But for data scientists, there may be situations where type 2 errors rates. The example I always think of is like advertising, right? Where the cost of doing some kind of intervention or initiative is cheap, right? And online advertising might be relatively cheap. Where if you're saying, well, we're going to do this campaign to get people to click on our ad, committing a type 1 error rate, right, it might be less of a problem than committing a type 2 error rate, right? So showing somebody an ad that might not click on it, no big deal, but not showing an ad where it would have been effective, right, could cost money, right? So the type 2 error rate, so you got to balance that, right? So type 2 error might actually have a cost, a sale loss, where the type 1 error rate is just the cost of showing that ad, which might be really tiny versus, what a potential type 2 error rate. So I just bring that up because I think a lot of textbooks still focus on that type 1 error rate. And a lot of what we do, right, as we're going to see, the p-values that are in the press all the time and that we kind of emphasize really are getting to that type 1 error rate. But we're also going to show how to do type 2 error rate.
But a lot of research, isn't that based on maximizing power, which is 1 minus beta, which is the type 2 error?
Yes, that is true. But nowadays, with sample sizes so large, power is almost going to be sufficient to detect small sizes. Yeah, so you are correct. When I do grant proposals, the type 2 error rate is of concern, and that's power. So you're correct, Juan. But I rarely see it reported in journal articles, right? We only report type 1 error rates. We don't generally report type 2 error rates. So that's kind of what I'm getting to. So it is of concern. And I actually have a Shiny app I'm going to show in a moment. I think one of the reasons, right? So if we think of hypothesis test as the criminal justice system, right? That's kind of what we're doing, right? So if a presumed innocent, right? That's a null hypothesis. We're going to presume some person is, they're presumed innocent. We're going to have a trial and decide whether or not we're going to reject the null and say that they are guilty, right? So the null is innocence, guilty. And so the question is, like, in that situation, what is worse, right? So a type 2 error rate would be declaring the defendant innocent when they are actually guilty, right? And at least the way I was raised, I don't know if this is necessarily true, right? I always thought that, well, it's actually worse to put declare a defendant guilty when they're actually innocent, right? And I don't know if this is true, but anymore, but at least that's kind of where I lie, right? So, and you have to decide for yourself. I don't want to kind of influence your decision there. right? And so here, okay, now we're going to talk about the two different types of distributions. So we have the null distribution. So what we talked about with the central limit theorem, right? We're saying that the sampling distribution is going to approximate the mean, or approximate the normal distribution, centered around the mean. And so we're going to call, if we have a standard normal distribution, that would be centered on 0, right? And I'm going to talk about a one-tailed test here. So if we go back here, right, to this example, note that the alternative hypothesis is that the sample is not equal to 0.5. So we have to consider values less than and greater than. You can technically phrase your alternative hypothesis as a one-tailed test. So I think it might be easier to use my first generation status, right? I come in with some information. So my null hypothesis is that there's no difference in college GPA between first generation students and non-first generation students. My alternative hypothesis could be that non-first generation students are going to have a higher GPA than first generation students, right? So I'm only testing one side, right? Do you see how it's, because I'm using a greater than in this case, right? So when I calculate a p-value from the area under the normal distribution, I'm only going to do it to one side. And that's what I'm going to do here. I generally don't recommend that unless you have a strong argument for doing a one-tailed test. I'm only doing it here because the visualizations I'm going to show are a little bit easier to understand. And then we'll show the two-tailed test, and hopefully you'll get there, right? So under a one-tailed test, right, our critical value where we would reject the null hypothesis is not 1.96, it's actually 1.64. So this blue area is 5%. So we put the 5% all in the right-hand side of the distribution, okay? So that's the null, right? This is what we're using to calculate our type 1 error rate, right? So when we get a critical value greater than if it was at exactly 1.64, we would reject the null hypothesis with exactly 0.05 as our p-value. That's our type 1 error rate, 0.05. If we got a critical value, we actually got 2, we would take the area above 2 and say, well, we're rejecting the null hypothesis. Our type 1 error rate is going to be something less than 5%. It might be 4 or 3%. I don't know what it is, but we could calculate it. All right. So then there's this alternative distribution. Okay, so here's the null, right? Centered on 0. It's centered on the null value. And so here I'm using 0 as my null. The alternative distribution now is still a normal distribution and it has the same spread, but it's now centered on our critical value. So right here, I'm using 1.64. So this is 1.64, right? And so that's where the the alternative distribution is centered. And here, the area to the left, right, of that critical value under this null is going to be our type 2 error rate or power. Okay, so let's look at them together, right? So if we have mu of 2.5, right, so our critical value for a 5% type 1 error rate is 1.64, right? So here's our null. We observe a value of 2.5, right? So our alternative distribution is going to be centered on our observed value, so 2.5, right? But our type 2 error rate is going to be from our critical value, 1.64, from whatever we decide we want our type 1 error rate to be. So the area to the left now becomes our type 2 error rate. Right. This is often sometimes called a beta distribution, but it's I think alternative distribution is a little bit better because beta, we're going to use that. We won't use it in this course, but there's a different kind of beta that I don't want to confuse it. Okay. So the type 1 error rate with a 2.5, right, assuming a standard normal, right? So our type 1 error rate in this case is 0.006, less than 1%. But our type 2 error rate is like 19.6%. Okay. And this is, as Juan pointed out, sometimes referred to as power. So let's look at, there's an interactive app here that my colleague wrote that I think might help here. So again, I'm going to turn everything off. So here you can decide your type 1 error rate. So let's just keep it at 0.5. You can then specify a null and an alternative. and then the standard error of the mean. We'll leave that at 5 for now. Okay, so our null is 100 and we observe 105. So that's going to be the center of our alternative. So if I show the null hypothesis, right, this hopefully is going to start feeling familiar, right? Centered on 100, right? That's my null, right? Standard error of the mean is 5. And so we observed a 105, right? Which would be right here, but we need a critical value. We need to observe something greater than 108, given these, this null, to reject it. So with 105, we would fail to reject the null hypothesis. So that's our type 1 error. So now I'm going to turn that off. Here's our alternative, right? So we observed 105, right? Which is right here. So that's where our alternative distribution is centered. And the area to the left of our critical value is our type 2 error rate. So given a situation like this, right, we would fail to reject the null hypothesis, but, oh, the little symbol didn't come through, but our type 1 error rate or type 2 error rate is 74%, right? Big possibility that we're not rejecting the null hypothesis, but it could, could be. So these, if you plot these things together, right, you can kind of see how they're related, right? So we have our critical value. The type 1 error rate is in a one-tailed test to the right of the null distribution. The type 2 error rate is to the left of the alternative distribution. All right, and so you can play around with this, but what I want to do real quick is go to the two-tailed test, right? So let me turn off the alternative. So when we go from one-tailed, right, you could see here, we're leaving this at 0.05 where we put 5% to the right. When we go to the two-tailed test, we have to push this out a little bit here. So now we have 2% in the red here and 2.5% and 2.5% here. Okay. And so when we do the alternative, I said to the left, but technically it's the area in between. So let me actually go down a little bit more here. Right. And I think if I turn off the null, right, now you can kind of see. So when we have a two-tailed test, the reason why I started one, because it's a little bit easier, I could just say to the left, but it's technically the area under the alternative distribution between the two critical values, right? And the type 1 error rate is the area under the null distribution outside the critical values, right? So that's the type 2, there's the type 1, and we could put those together. And so what we could see is as we increase it, right? So our type 1 error rate is going to get, well, we got it fixed at 0.05. And this here, I think is supposed to, yeah, that's I don't know why the label's showing up. That's the type 2 error rate. So as we get up, as the difference gets greater, right? Our type 1 and type 2 error rates are going to get less, and we can kind of see how that area gets smaller and smaller. Questions? I want to pause, make sure that that's clear. All right. Back to the slide deck. All right, so why 0.05? I have a little, so I have this app, it's in the data 606. I have this little Shiny app. It is arguably arbitrary, and I will admit that, but there is some sense to it. And so in this app, I really encourage everyone to kind of run this later on your own and answer the questions yourselves. It's a little hard to do on Zoom. When I do it in person, I kind of take votes with thumbs, but I'm just this is going to be my threshold. So for each scatter plot we have here, I need to decide whether or not I think there is a positive upward trend or not, right? So my null is that there is no real trend, or, but if I think there is, I'm going to reject the null and say there is, right? So I have two buttons that I'm going to decide here. So on the first one, I'm going to say there's no trend. I'm going to say there is a trend, no trend. Oh, this point is throwing me off. I'm going to say there's an upward. Oh, definitely no. I'll say yes, no, 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 no. Maybe, but I'm going to say no. I'm going to say no. Okay. So here we are. So we're going to talk about correlations, but that's kind of what we're doing here. So we could see this is the table. So here are the scatter plots. So 3 of them actually had a statistically significant correlation at you presuming a p of 0.05. So in other words, the correlation is statistically significant at 5% or less. Okay. These are my responses. So the first one had a correlation of 0.6. The p-value was 0.01, and I didn't think it had a trend, which is kind of interesting. Then I said there was no, and then I had true. But notice that when the p-value was greater than 0.1, I didn't say there was a trend at all, right? So for me, these are kind of oddballs. I should update this to actually be able to see which scatter plot was which. So for me, maybe my threshold is maybe more like 0.1. But if you go to the slide deck, there's an article here that you can look at from significance. And people have done studies on this. And this is just one little silly example. There are other ways to do it, but somewhere between 5 and 10% seems to be approximately where human beings kind of settle or can detect differences. All this to say 5% confidence, 95% confidence intervals having 5% type 1 error rates is admittedly arbitrary, but there is some, human intuition that, puts us or makes that a kind of a reasonable threshold to have there. Do you have anything to add to that, Angela? I'm resisting going into my p-value rant right now, but I'll save that for another day because they are kind of useful from time to time if you use them appropriately.
Yeah, they're useful also because people understand it. I mean, it's been used for so many years, for so long that that's the go-to for statistical.
Yeah. Every few years, there's a special so I'm sorry, Juan, and then I'll let you. Every few years, the debate on p-values kind of grows again, and there's
the p-hacking.
P-hacking is a problem, for sure. And then it's about 3 years ago, some journal, I can't remember the name of it anymore, made news because they would just banned p-values from all publications in the journal. And then people are like, well, is that really, it's like, are you throwing the baby out with the bathwater kind of thing? But p-hacking is an issue. Were you gonna say more about that one?
Yeah, I was gonna mention Ioannidis' article about why most research is wrong. I think you probably read it, right? All of you.
Yeah. And there's this so-called psychology replication crisis. You could argue, people argue that, well, at least 5% of published articles are wrong, right? If we're using 5%. Which is why replication is so.
Well, he claims
important.
more, right? He claims that you repeat the test 20 times, and then you find one of them will hit, and that's the one that gets published. It doesn't get published the other 19, right?
Yeah. I mean, that is I often criticize meta-analyses for that very reason, because meta-analyses are, by virtue of publication biased. So, getting non-significant study results published is much harder. But yeah, I think he's a little sensational. I think there are issues. I don't think it's as bad as he states, but there are issues. My advice is just I like confidence intervals, which are really kind of doing the same thing, but they give you a sense of the range of where the value can be, right? So p-values just end up getting interpreted as, reject or not reject. We dichotomize it. And I think that's the bigger problem, is you just end up with this arbitrary, dichotomization. And because the square root of n is in the denominator for the standard error estimate, as n gets larger, the standard error is going to get smaller, right? You're making the denominator bigger. So that's another problem. where, when these methods were first being developed in the early 1900s, sample size of 30 was huge. Now we think nothing of sample sizes of, 30,000 or 30 million if you're in, some of these Silicon Valley companies, right? So, so confidence intervals give you a sense of, it's more than just a yes, no, it's kind of a range. And if you have a very small confidence interval, right, then you can interpret that in some way. It's probably because of big sample size or something like that. And I think, yeah, here we go. Next slide. Look at this. Statistical versus practical significance, right?
Mhm.
And what's really interesting is, Angela, on our current grant, one of the big things we had to include is a cost effectiveness analysis. And so this is kind of how the Department of Ed is trying to handle this, where, we're going to, you took the self-regulated learning assessment from DAX, right? So we have a whole system where there's other assessments, there's feedback with students, right? And, we're hoping to increase student success, particularly in the first semester, right? By giving them this feedback, and this information goes to academic advisors. How big of a difference, right? I mean, in our power estimates, we're expecting small differences, but our intervention is really cheap, like to implement. If you think about a per student cost, right? And so cost effectiveness kind of tries to deal with that. If you have a very inexpensive intervention that has small changes, that's good, versus an intervention that costs a lot of money. I saw colleagues, right? And one way you can increase retention is hire more academic advisors, but academic advisors are expensive, right? You got to pay a salary and et cetera, et cetera. Now, what's interesting is there's research for a lot of institutions where, yes, it's an expensive intervention, but the lift in like retention is so large that it more than pays for the cost of additional academic advisors. So if you can get, so I don't know what, so tuition at CUNY is $5,000 per semester. So if you call it 10,000, 10,000 per student, and you hire one more academic advisor, and you get, let's be generous, 10 more students to be retained, that's potentially $100,000 additional dollars that institution can bring in, probably more than what the salary and benefits, maybe not, but 100,000 with salary and benefits is probably reasonable for like that kind of position. So that's only 10. You have to get 10 more, right? So tiny effect sizes, but they can pay for themselves. So anyways, all that to say, you got to kind of look at the practical versus the statistical in that. Okay, questions about that? And the story, I always mention is I actually don't have a single p-value in my dissertation. I did use confidence intervals, and I had a couple of pages in my discussion section justifying why I don't have p-values, because I wanted to make that statement. But I readily use them when necessary. So it's not a hill I'm going to die on anymore. Bootstrapping. And this, Diana, I sent some questions ahead of time, so I want to get to your questions. Some of them seem to be related to the bootstrapping piece, so hopefully this will help. So bootstrapping was originally introduced by Efron in 1979 in a paper. I think there's a book. There are lots of R packages to do this, but it's actually pretty easy to just code up yourself. And the goal of a bootstrap is to estimate the sampling distribution. And we're going to do it using simulation. So now with the advent of really fast computers in R and Python, we could do this really easily. So going back to our population, so here I redefined it. So I could take, obviously I could take one. Usually I have one random sample. In this case, I took one of size 50. All right. So what a bootstrap sample is going to do is I'm going to sample from my sample with replacement lots and lots of times. Okay. So the with replacement is key. So let's walk through the code here. So I'm going to initialize a vector that I'm going to save the mean from each bootstrap sample. And I'm going to start with 1,000. And this is a common approach. I usually start when I'm doing analyses I might even start with as little as 500 to get it to run. And then when I want to get a final answer, I'll make it big, right? And go get coffee and wait for it to run, because sometimes it's going to take a while. Although bootstrapping is an easy thing that you can parallelize if you have like multi-core machines. Right. So we have a vector initialized, it's empty. We're going to loop through it. And each time I'm drawing a random sample from my sample, right? This guy, right? Of the same size, right? So if I just called sample like this bit here, all I'm doing is shuffling the values in the vector, right? But there's this parameter that says replace equals true. So what this means in like say take my first bootstrap sample. So this is going to be called a bootstrap sample. Some values are going to appear more than once and some not at all, right? And that's really important. So so we're sampling from our sample, and here I'm just saving the mean. And you can see here I'm looking at the first 6 values, but let's look at the distribution. So this is after 1,000, right? So my bootstrap sample is going to approximate the normal distribution, right? So now my standard error calculation is not, using the standard deviation of my sample over the square root of n. It's simply, 95% under this area, right? I could just read it directly, which I think I have on the next slide, right? So here I'm taking the mean minus 1.96, right? I still know that it's normal distribution, that's my critical value, times the standard deviation of my boot samples vector, which is my bootstrap samples. So I'm literally taking the standard deviation. The standard deviation of this distribution is an approximation of the standard error. Okay, and this is really, really powerful for a number of reasons. The estimates tend to be more stable than just using standard error, because for one thing, the presence of outliers are the influence of outliers are diminished, right? Because the likelihood of them appearing multiple times across multiple bootstrap samples kind of diminishes their impact. It also helps with skewness, right? So skewness issues will kind of even out when you have more bootstrap samples. So this becomes really effective. But it's also really effective because it allows you to get confidence intervals for metrics that don't have well-defined confidence intervals, right? We know the standard error for a mean, but what's the standard error for a median, right? Where you want to look at the median. Well, here I could say this is all set up as the same. The only difference between this slide and this slide is right here. I'm saving the median instead of the mean. And so now I have a confidence interval for my median, and this distribution is still going to be normal. Okay. So very, very powerful and effective way of getting estimates for confidence intervals and p-values by just taking samples from your sample.
But you still depend on that first sample not being an extreme example, right? I mean, if you just were unlucky and you pick the first sample of 50 and it just by luck it was an extreme one, you're just going to generate a normal curve around a very extreme value.
Sort of, but it would have to be pretty extreme. It would be beyond sort of the 5%. And I might make a note that we could do a simulation and force a bad sample. Yeah. This, and I don't want to go down this rabbit hole right now, because there's a similar criticism of like Bayesian methods, because it's kind of similar to a prior, right? But the prior is picked by the researcher, where but it turns out Bayesian's pretty robust to bad priors. So the bootstrap method is fairly robust to violations in that way, more so than just using the standard error calculation that you would normally do. So the reason being, like, if you have a large, so in this case I did 50, right? If you have a large enough sample size, it's not just a couple of outliers. You're talking about the whole distribution being an outlier, and I think that the compound likelihood of that happening is much smaller, right? But point taken. All right, let's review last couple slides here. So where did we start? We started with a population distribution that is uniform, right? So I guess I picked a different one here where the have value uniform between 0 and 5, and so the mean is 2.5, right? So that's kind of what we're trying to estimate the center. Okay. So I often take one random sample. That's what I observed, and that's what we show in blue, right? I took a random sample here, and so I shaded 95%. So 95% of the values from my random sample are in this shaded area, right? And from there, what we want to do is estimate the sampling distribution. So this red line is given this blue sample, right? So it's centered on the mean of my sample, and then I shade 95% around it, and I'm saying, oh, I'm 95% sure the population mean falls within there, right? So this is the sampling distribution that we get from the central limit theorem, but then we can do a bootstrap, which is what's shown here in the green. And here I'm just going to take 95% of the area of the bootstrap sample, and you can see in this example, it does indeed capture the center. So I just like I like this figure because it shows sort of the 4 different distributions we were really focusing on one plot, right? Where we start wide, right? And we get to the sampling distribution where really, so what we're trying to do with the sampling distribution is just narrow in around the mean of that value. And where is that mean that we have from that distribution? Okay. All of this approach, and we're going to kind of continue this in kind of more complex ways, is part of what's called a frequentist approach, right? So when we talk about frequentists, what we're saying is we're making inferences based upon, relying on the central limit theorem that the sampling, that there exists some sampling distribution that approximates, in this case, the normal distribution. Now, we're going to extend this to other types of distributions. So if we have qualitative variables, there's a central limit theorem that's going to say they're going to estimate different types of distributions. So we'll talk about that, I think, next week, I think is qualitative, and then the week after is more quantitative. Okay. So these are all 3 at the same time. Look at that. We got about 7 minutes. I'm going to throw this in. I'll take questions. But I know Diana sent some ahead of time, and I brought up this screenshot because this is one of them that was related to the Lab 5. Let me close that one. I thought I opened it up. Oh, and it locked me out. So I don't know where to start. I could start with Diana's questions, or if somebody else has questions. Noah, I see Noah, you got your hand up.
Yeah, thanks. I have 2 questions. One is, you sort of said bootstrapping is good for, I forgot the word you used, diminishing the effect of outliers, I guess is what you said.
Yeah.
Can it have the inverse, where if there's a mode data point, like one that's especially pronounced, that'll sort of get over exaggerated?
Yeah. I mean,
with replacement. So if there's one data point that's more prevalent.
Yeah. So if you have 2 outliers, right, that you got some bad luck. If you have 5 outliers, you're in even worse luck. But then this question, if you have a bunch of outliers, are they outliers anymore, right? So the reason being is, and I should have it develop an animation. I can kind of visualize it, but but yeah, the mode is, if particular values appear more than once in your sample, then of course the likelihood of that value ending up being a bootstrap sample is increased. But it's only a problem if the mode is a value that is skewing the distribution in some way, either causing skewness or an outlier, right? And having 1 or 2 outliers is one thing, right? And so in a lot of samples, they're not going to be included. In some, they might be included more than once, but so are other things. So, I mean, if you look at the figure here, and I don't remember how many bootstrap samples. I have to go look at the source code. Note that the 95% confidence interval for the bootstrap is smaller than the standard error, right? Because you can just draw more bootstraps and it's going to kind of stabilize a little bit more too. So I'm not sure if I completely answered your question, but hopefully I'm talking around it enough to make some sense.
Yes, you did. Thank you. I had a second question, which
Yep.
was about the type 1 and type 2 errors. You know, with advertising example or another one, there's sort of an assumption that you know the truth. So, or even with the jury, you know, it's bad to convict someone if they're innocent, but sometimes no one knows if someone's innocent, or in the advertising example, no one knows if he would have hypothetically clicked or not. So there's sort of, is there sort of some odd philosophical point where you just have, you don't know what would have actually happened?
Well, I mean, statistics is really the measure of uncertainty. A real statistician will never say for sure one way or another. What we say is the evidence currently suggests this, right? And so we're trying to get to truth, but recognize we can never really get there. And even if you take, lawsuit example, right? There are different standards, right? So for criminal, right, it's beyond a reasonable doubt versus civil lawsuits are preponderance of evidence, right? Or something like that, right? So in essence, you're setting different p-values or thresholds to reject the null, depending on whether or not it's a criminal or a civil trial, right? And so even in that example, yeah, like I said, if I'm, if I'm evaluating a cheap intervention, I might accept p-values all the way up to 0.1. But if I'm doing a drug trial, I might want to be even more sure. I might set my threshold at 0.01, right? Which is often common in the drug research world. You want to be really sure because a type 2 error rate might be death. But on the same token, you can have very small effects, right? Where if you're talking about a drug that may have minimal side effects, but its effectiveness is really small, but you multiply that out, you have 1 million people that have this disease, and you have an effect size of 0.1, that translates to potentially thousands of people's lives, right? So in that case, the type 2 error rate might also be of concern, but you got to weigh that against what, potential harm on something like that. So I guess all that to say is you got to know your domain and what are the standards of evidence for your particular domain to set those thresholds. So I talked a little bit about I'll say it again, 0.05 is completely arbitrary, but there's some reason why we landed on 0.05, and certain fields will have stronger or less strong criteria to reject that null hypothesis.
This is also the reason Jason said we never say we are trying to prove something, right? We reject a null, and it's because we don't know. We don't know the truth.
Don't use the word prove. You're not proving anything. You're providing evidence.
Yeah, great. Thank you. That is helpful.
And that was so real. My undergraduate was in pure mathematics, and so I used to be of the mindset oh, those statisticians, we're actually proving things over here. You're just when I was young and stupid, and now I end up as a statistician, but but that's the way the world works, right? Human beings are complex. The world is complex, and we don't really prove things. You can prove things if you live in an arbitrary rule where you can define all the rules, right?
Well, if you believe Karl Popper, he said that you can not only prove things wrong, right?
Yeah, yeah. And then you have Box, who said all models are wrong, but some are useful, right?
Yeah.
And I like that sentiment quite a lot.
Yeah, I like the other one that says, that science only progresses when you keep proving all theories wrong.
Yeah, well, that's how a lot of people try to make a career. I mean, in fact, our colleague David, right? You could think of his dissertation in some way. There's all this hubbub around grit and mindset, and it may be a lot of do about nothing. It turns out, at least with our student populations, there was no effect there. And there's sort of a cottage industry now in educational research to kind of shoot down grit as something, which is unfortunate. It's a psychometric wonder to me that in 10 items there's still some prediction value there. But anyways, I digress. All right, Diana, I need some clarification on your question. So one of them was related to this figure, and you're pointing at this, and so you had a question about why some things are red, because it looks like these are exactly on. And of course, if I run it, I get a different set of lines. So that's why I pulled yours up.
Yeah, no, I mean, I ran it a couple of times and this only showed up once.
So,
but I was curious. I also have a hard time figuring out exactly what the boundaries are because, it's small and I don't know exactly what the numbers on the points are. But
yeah. So this
my question here is
it this one right here that looks like it's touching the line, but is still green? Is that the one you were referring to?
No, it's the red one.
Okay.
Right. So the red one looks like it's touching the line,
Mhm.
which means that it should be green, I would have thought. But then when I looked at the code, it said greater than or less than, for figuring out which color it should be.
Yep.
And I wondered if changing it so that one side was greater than or equal or less than or equal, either way probably would work.
Yeah.
And maybe it's not really touching, and that could be it too.
Yeah, I think that's probably what it is. It's probably a visual anomaly that you're seeing. Although, help me out here, Angela. What if you get? So I know there's an XKCD p values. I'm pretty sure it's XKCD. Yeah, here we go. I should put this in the slide deck, right? So we're talking about right here, if you get exactly 0.05, what the hell are you going to do? I like this. Oh crap, redo calculations. Because I think typically we say less than 0.05. So if you get exactly 0.05, you suddenly want to round down, or it's like
some people like to use, say, borderline significant.
Yeah. So I think it's just a visual anomaly. I'd have to go look at the number.
It was just making me not sure that I understood what the chart was representing.
Yeah, I would. Oh, I lost it. Yeah. So here's how I would interpret this. Don't sweat. So if it's red, I'm assuming the calculation under the covers is correct. If it's red, it doesn't span the mean, the value, right? And so
I will say that I did have examples where everything was red, and that was because they all spanned the values. There were no no's, and then they all came up red, which was confusing until I realized that. So if you get all yeses, they come out all red.
Okay. Well, I gotta look at that.
But it's still showing it correctly because you have the legend on the bottom, and it says red is yes in that case.
Yeah.
It just takes a minute to get to that.
Yeah. So I would just interpret it that way. So the way I like to look at these, right? So here, this is doing, this is doing bootstrap. Okay. Right. So, you got 50 here. I always like to go to 100 because it's easier for me to do the arithmetic. So if I'm doing a 95% confidence interval, I would expect roughly 5 of the lines to be red and 95 to be blue. So here, I would expect half that, right? So I should get like 2.5 lines, and you have 5 here, right? So, but if you rerun it each time, you're going to get a different answer.
No, running it multiple times was sort of interesting, which is why I found things like this.
Yeah. I think this is just it's so weird that this figure has 1, 2, 3, 4 that just seem to fall exactly on the line. I might dig into it, make sure there's no error in the code, but I'm just, yeah, going to this, we want less than. So if it's exactly,
Okay.
I got to look at for this particular question, I can go look into it. So I'm going to guess there's some kind of measurement error that is causing it to round so evenly. That sometimes when we don't talk about that enough, the issues of measurement when we make these kinds of inferences. So that answer, hopefully, probably didn't answer, but did I give you a little bit? There were parts to it. Did I get all of them? I think that's what you were.
So that was the third question. The first question you answered in the context of the lecture.
Great. That's what I was hoping.
And the second question was just sort of to understand what you're asking. So in 5B, exercise 6, you ask us to explain our observations and then say, make sure we include a plot in our answer, but we're using your Shiny app.
So just grab a screenshot.
What are you expecting us to do?
Yeah, just grab a screenshot. Yeah.
Or never would have occurred to me to do a screenshot. Okay, thank you.
When you're running the Shiny app, if you're running it in your browser, you can take this picture and right click on it and save it from the Shiny app. So you don't even have to do your screenshotting thing. This is just an image that you can save. Yeah.
Okay.
So we haven't talked about random numbers and seeds yet, have we?
We have talked about seeds.
Seeds. Okay, we did talk about seeds. Okay. I have a little article I could probably post on the website that just computers are actually pretty bad at generating random numbers. So there are what are called pseudo random number generators, and they rely on a seed. And so you kind of get random noise. And I have a little bit of R code that I, increment setting the seeds like from 1 to 100, and then you plot them, and you can look at the correlation between the seed and sort of a Y value, and the correlation is pretty, should be pretty close to 0. And anyway, so that's what so seeds are often set to something like the time in milliseconds, right? Which is when you click execute is roughly a random event, right? In terms of differences in milliseconds. So that works actually fairly well. But when you have bad number generators, if you follow anything in the crypto world, understanding seeds could be a problem. Like, so if you have, everybody probably has 2-factor authentication now, you're probably using Google, Authy or Google Authenticator, right? And it just gets the number. The way that works is when you set it up through a QR code, you're given a seed. And with that seed combined with the time can generate that number. So you don't need internet access. It's all kind of built in, and it's, kind of predicated on this notion that we shared this seed really a long time ago at some time, and we both know the difference between that number, that time, and now, and we can put that into the random number generator, and we can get the same answer on both sides without actually communicating with one another, right? And so if you figure out the random number generator, then you can reverse engineer it and break the encryption. Right. And that's what a lot of people try to do. And so you have bigger ones, and it's probably an oversimplification, but in general, that's kind of what's going on. Okay, great. Other questions?
Quick one. If I click on the 1 minute paper, there's only one chapter 5. So are we going to write over or repeat it?
Yeah. So yeah, you can just pick chapter 5 again, and you can submit it again. And I'll look at them. We'll look at them combined next week and try. Do you still have a question, Noah, or is that your icon didn't go away?
No, sorry.
No worries. No worries. I just want to make sure I don't miss you or anyone else.
And I have a fluff question for you. I think somewhere I saw you had written that you're an assistant processor instead of an assistant professor.
Oh, where did I write that?
Is that a joke?
No, that's a typo. Where is it?
I'll find it. I think it's in your bio for Slack, or it's on your GitHub or something. I'll find it and tell you.
Oh, Jesus, that's embarrassing.
I didn't know if that was an inside joke.
No, that's good. No, okay there. Of course, I never see my bio in Slack. I don't know how to see that.
no worries. I'll find it and tell you.
Oh, that would be wonderful.
Um,
I'll be curious to see how long it was there. Because sometimes some of these typos last a long time. And like, how did I not see that? I look at it all the time. Could it be here? No, it's okay there. All right. Well, if you find it, let me know. Thank you. I wish I was so clever. Yes, I did that on purpose.
Yes.
Forget what I said. It's in Slack. Thanks, Justin. I got to figure out how to see that and change it because I never see it. All right. Any other questions about this? I don't know how it would ever exist in a non-spell check, world. Maybe I would have learned to spell. Right. All right. Well, then let's call it a night. Thanks, everyone. We'll see you next week.
Thank you.
Thank you.